welcome to Quarter 4 Review. The quarterly will be held on Tuesday, June 10th of next week. The units you need to be familiar with for the quarterly are acids and bases, electrochemistry, organic chemistry, and nuclear chemistry. Let's get started with acids and bases. To start with acids and bases, you have to first be able to identify and define an acid and a base. So according to Arrhenius, you might see his name. Arrhenius is the name of the first person who came up with the concept, the definition for an acid and a base. And he said that there were certain ions that an acid yielded in solution, and that was different from the ion a base yields. The ion an acid yields in solution is an H plus ion, or it's also called an H3O plus ion. So the two ions are either a hydrogen ion, or if you look on table E, you would know that this is called a hydronium ion. It is important that you know how to represent the formula for these particular ions and how to name them. A base is another H word, so it's an OH minus ion, which is called a hydroxide ion. So if you were asked a question that said which of the following yields a hydronium ion in solution or an H plus ion in solution, I flipped the page for a second, you would choose any of the acids on table K. Notice the organic acid at the bottom, right? This is ethanoic acid because it has the two carbons, and that's the only one where the H isn't written in front of the molecule all the time. Although notice that it can be written in two ways, which the H in front of the molecule or as COOH, like we discussed in class. Oh, if you were choosing a base generally has OH minus. According to Arrhenius, it yields OH minus in solution or hydroxide in solution. Bronsted-Lowry, you have to remember to define an acid. Remember, we defined an acid as PDA. That means that it was a proton donor acid. That was the way to remember it. And the proton donor, what is a proton? A proton is just an H plus because it has one proton, 0 neutrons, and 0 electrons. Check me and make sure you understand that H plus is just a proton. A base, on the other hand, is the H plus acceptor. So if something donates, something else accepts. So if you look here, if we did NH3 plus H2O yields NH4 plus OH minus, you would notice that if you look at the NH3 and the NH4 plus, as the reactants go to products, the NH3 gains an H plus. Well, where does it get it from? It gets it from the H2O because the H2O donates the H plus and becomes OH minus. So in this case, the acid, the Bronsted-Lowry acid would be water, and the Bronsted-Lowry base would be NH3. As I said, to identify common acids and bases, you would look on table K and table L. They also tell you how to name them. Take a look at HCl. HCl is hydrochloric acid. Notice that if you had to use that pattern to name like HF, for example, you would maintain the same pattern. It would be hydro instead of chloric, fluoric acid. So you would just maintain the pattern that you find on table K. And then the bases you would name the same way as you would name ionic compounds. So for example, the first one is sodium, and then the second part of the name is hydroxide. The one weird base on the table, it's a Bronsted-Lowry base, is NH3, and that's called ammonia. One thing to remember we said that you can scream at the alcohol because they always put an alcohol in there to try and trick you to make you think that it's a base, but it's not a base because it's not ionic. So because it's not ionic, it's not going to ionize in solution. So it is not a base. It won't yield OH minus. So you have my permission to scream, you are not a base if you see that alcohol on a test. Do not get fooled. Also, please remind yourself that an electrolyte can be an ionic compound or an acid or a base. Why? Because when they dissolve in water, because there are moving ions when they dissolve in water and they form a solution. Anytime there are moving ions, you are going to have an electrolyte. How do you get the electrolyte? You need either an ionic compound, any acid, or any base. Now, what kind of reactions do you have to know involving acids and bases? Well, the first type is a single replacement reaction where the metal, if it's higher on table J, very important that you look it up on table J. If it is more active than hydrogen on table J, it will kick the hydrogen out of the acid formula and form hydrogen gas plus an ionic compound, a salt. So let's write the formula, let's write the equation for magnesium plus hydrochloric acid. If you don't know what that is, look on table K, plus HCl yields. Now, magnesium is higher on table J. I checked. That magnesium is going to kick the H out. Now remember, H is a diatomic. So it doesn't just form H. It has to be H2. It's never going to appear by itself in the reactants or the product side of the equation. Now, what is our next formula? What's the other product? Well, we have magnesium and chloride. But remember, by the law of definite proportions, we just can't stick them together. We need to use our crisscross method. We realize that magnesium is in group 2 and has a positive 2 charge, and chlorine is in group 17, so it has a negative 1 charge. Cross out the charges, crisscross the numbers, you get MgCl2. So our other product is MgCl2. Now we have to balance the equation. If it asks us to balance, we have 2 chlorines on this side, so I'm going to put a 2 here. That gives me 2 H's, and we are balanced. So this is the first type of reaction that acids are involved in. The second type is called a neutralization reaction. Neutralization takes the form acid plus base yields salt plus water, always. So let's take a look at how this works. Well, if we have nitric acid, I can write the formula based on table K, HNO3. Nitric is 8, remember NO3 is 8, plus potassium hydroxide. I can look on table L. Now, how do I figure out what the products are? Well, this is neutralization, but it is also just a wife swap. It is a double replacement. So I have to figure out what ions are in each solution. In each compound. So in the HNO3, we know that it's an acid, so it ionizes an H plus ion. Plus, we can look on table E and see that NO3 nitrate is also formed. That's the polyatomic. Table E helps us to figure that out. And here we have a base, which is K plus, and we have the ion that is yielded in solution for bases, which is OH minus. Now, when we do the wife swap, we actually physically cross out the positives and change their places. Now, when we go to write our new formulas, we have plus 1 minus 1, which is an even proportion. So we know we have 1K and 1 NO3. And then the same thing here. We have H plus and OH minus, so we have HOH or H2O. Now, I prefer to keep it as HOH when we're going to balance our equation, because if you notice, we have 1 OH on this side, and we also have 1 OH on the reactant side, so I know that's balanced. We have 1 other H, that's over on the reactant side. We have 1K, and we have 1 NO3. So this is already balanced. What are the names of these products? Well, KNO3 is potassium. And then if you look up on table E, nitrate plus water. And that's what we said. Acid plus base yields a salt, which is an ionic compound, and water. Good. Okay, now the pH scale. When you're asked pH questions, you need to draw yourself a diagram. So I would draw a line and I would put 0 on one side and the highest pH, 14 on the other. I would actually physically write that an acid is at 0 and a base is at 14. Then I would remind myself acids have increasing concentrations of H plus or H3O plus, and they have decreasing concentrations of OH minus. Whereas on the other end of the spectrum, the base has increasing concentration of OH minus and decreasing H plus or H3O plus. The other thing that I would do, this is going to sound really silly, but I would write the pH increases because it gets confusing, these words. So I would write pH increases as you're going more towards a base, and pH decreases as you're going more towards an acid. Okay? So then the other thing you need to remember is that the pH is a logarithmic scale. Remember, pH equals negative log of the H plus ion concentration. So pH is all about the H plus or the H3O plus concentration, and it's logarithmic. All you need to know about that is that each jump in pH represents a tenfold change in the H plus ion concentration. So if you are getting more acidic, you're going to increase the H plus ion concentration 10 times for every jump. And if you're getting more basic, you're going to decrease the H plus ion concentration. So look at question number 1. How much stronger is an acid with a pH of 3, so I'm going to draw that on here, pH of 3 than a pH of 5? Well, it's going to be more acidic, 3, because it's more towards the acidic end. How much stronger is it? Well, each jump, because it's logarithmic, is 10 times greater. So it is 10 times 10, it is 100 times greater, meaning it has 100 times greater concentration of H plus ions or H3O plus ions. Just some other questions. Which pH value indicates the most basic solution? That would be 11 because it's closer to 14. And which pH value represents a solution with the lowest OH minus concentration? Well, the lowest OH minus concentration is going to be down at the acid end of your graph. So you need the lowest pH number. That would be 1. Okay, table M. Turn to table M. Table M teaches us about indicators. An indicator turns color or different colors in the presence of different pHs and different strengths of acids and bases. So if you have a liquid that turns blue in Bromm-Krieskal green, let's look at it. So here's Bromm-Krieskal green. The way we read this is if the pH is 3.8 or less, the color is going to be yellow. If the pH is 5.4 or greater, the color is going to be blue. If it's in between 3.8 and 5.4, it's going to be green. So it says a liquid turns blue in Bromm-Krieskal green. So if it's blue in Bromm-Krieskal green, it has to be 5.4 or greater. Okay. And then yellow in thymol blue. So let's find thymol blue. Thymol blue is yellow when it's 8.0 or less. So what is the range of possible pH values? From 5.4 to 8.0, somewhere in between those two, because it has to be greater than 5.4 or less than 8.0. Number 2, what color would a solution of pH 4.5 be if it was in contact with Bromm-Krieskal green? Okay, 4.5 is right in the middle between 3.8 and 5.4. So what color did we say it would be? Right in the middle would make it green. Finally, what color does ammonia? You should have bells going off in your head. Ding, 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 ding. Ammonia is a base, right? It's on table L. What color would it be in phenolphthalein? Well, a base in phenolphthalein is most likely going to be, at the higher pH level, most likely going to turn pink. In litmus, it's most likely going to be blue. And in methyl orange, it's going to be at the upper end of the scale. It's going to be yellow. Okay, now solving problems that have to do with concentration for acids and bases. First type of question that you could get, for example, is just to figure out the concentration of, or the molarity of, a solution of an acid or a base. For example, take a look at number 1. What is the molarity of a solution that contains 4.0 moles of NaOH in 50 milliliters of solution? So we're given moles and we're given milliliters. So, and I know I'm looking for molarity. So I look, and there are two possibilities. There's molarity formula and there's the titration formula. In this case, I realize that molarity equals the moles, which is what I'm given, of solute over liters of solution. So I'm given moles and I'm given milliliters, but I am given a volume. So this is the formula I'm going to use. How many moles? 4.0 moles divided by, now I have 50 milliliters. I need liters. So I do kids hate doing units during certain months. I have milliliters. I have to go to liters, which are units. 1, 2, 3 places to the left. Put my pen down. 1, 2, 3 places to the left. 4.0 divided by 0.050 liters. I do the math, and everybody do the math. Okay, I do the math, and I get 4 divided by 0.05, and you get 80 molar. Okay, 4 divided by 0.05 gives you 80. All right, now that's different from this second problem. What is the concentration of a hydrochloric acid solution in 50 milliliters of 0.25 molar KOH, and it's needed to neutralize 20 milliliters of HCl solution of unknown concentration? We're looking for concentration again, but we have this keyword neutralize. So you go, I know what to do. Instead of using this molarity formula, when you have the words neutralize or titration, we have to see if maybe we should use the titration formula. MAVA equals MBVB. Now, the one thing to be very careful with in the titration formula is, remember, the molarity is molarity of H plus and OH minus, not of the acid and the base by themselves. So, for example, the way I would solve this is I would put my acid on the acid side and my base on the basic side. And then I would write MA, VA, MB, VB. Oops. Then the first thing I do is, how many moles of H plus are there? Well, there's one of them. So I know I have to multiply whatever the concentration is by 1. And how many moles of OH minus? One of them. Okay? Then I have to figure out what I have. I have 50 milliliters of 0.250 molar KOH. So my molarity of KOH is my base. I have 0.250 molar, and I have 50 milliliters. On the other side, I have 20 milliliters, but I don't know what the concentration is. Now I need to solve. I put in 1x times 20 equals 1 times 0.250 times 50. And I'm going to let you solve it the rest of the way. Okay, electrochemistry, assigning oxidation numbers. Okay, 3 ways to do it. First of all, if it is just an ionic compound, the oxidation number is the same as the charge. right? So we could look these up. Magnesium is in group 2, so it's +2, and oxygen is group 16, and plus we know that oxygen is always -2. So the oxidation number is +2 and -2. Now, H3PO4. I'm going to show you two different ways to do it. I'm going to do H3PO4 one way and aluminum sulfate another way. Okay? So with H3PO4, what I'm going to do is I'm going to set the whole compound equal to 0 because there are no charges. I'm going to say the oxidation number of hydrogen is always +1 unless it's combined with a metal. So to find the charge, +1 times 3 is +3. I don't know phosphorus, and there's only one phosphorus, so I'm going to say +X. And then I'm going to say, okay, oxygen is a -2 oxidation number, so -2 times 4 is -8. Now, to solve this, -8 plus 3 gives me -5, so x minus 5 equals 0. X equals 5 because +5 plus 5. So phosphorus has a +5 oxidation number. So +1 plus 5 minus 2. The last one we're going to do is a little bit more complicated because of the parentheses. So we have aluminum sulfate. Now I'm going to take advantage of this idea of using a polyatomic ion. So the first thing I can do is set the whole compound equal to 0. But I know aluminum always has a +3 oxidation number because it's in group 13. And so +3 times 2 is +6. And I'm going to treat sulfate as a whole for now. And I'm going to say sulfate on table E says it has a -2 charge. So -2 times 3 is -6. So altogether, I've already set the charges equal to 0. Now to get the sulfur, I'm going to focus on the sulfate ion. So I'm going to pull out the sulfate ion, and I know the sulfate ion has a -2 charge. So instead of setting the ion equal to 0, I'm going to set it equal to -2. Then I know oxygen has a -2 oxidation number. So -2 times 4 is -8. And sulfur, there's one sulfur, so again it's X. Add 8 to both sides, and I get the answer X equals 6. Okay, so aluminum is +3. These are the oxidation numbers up top, by the way. Sulfur is +6, and oxygen is -2. Okay, oxidation, reduction, half reactions, and net ionic equations. Oxidation, okay? So oxidation, remember you have to take into account Leo, the lion, goes grrr. Please include Leo in your thinking. In fact, I would write down Leo, the lion, goes grrr. Now, I would notice that the Ag has a +1, and it's decreasing oxidation number to 0. When the oxidation number decreases, the substance in the reactants is being reduced. So this Ag +1 is being reduced, which means by Leo grrr, G-E-R, it's gaining electrons. The chromium, if it's all by itself, has a 0 oxidation number. It's going to +3. The oxidation number is increasing. If the oxidation number is increasing, it's losing electrons. It's being oxidized. Oxidation. It's being oxidized. And so by Leo grrr, it is gaining electrons. Now, in order to write the half reaction, simply draw the arrow where it is. Okay, let's do oxidation first. So we know the chromium is what's being oxidized. So we pull it down exactly as it is, Cr0. And then on the other side, we pull down exactly what the charge is, Cr +3. If it was attached to oxygen, we leave the oxygen off. If it was in a compound, all we care about is the chromium. And then we have to balance the charges. So we have +3 on this side and 0 on the reactant side. So we add 3 electrons to balance out the charges. For reduction, we have Ag +1. We bring down the Ag. And on the product side, Ag0. Now to balance out the charges, we add an electron. Finally, we want to write a net ionic equation because you have to balance equations for mass, charge, and energy. And we see the number of electrons lost has to equal the number of electrons gained, right? So we have 3 electrons lost, but we only have 1 electron gained. So in order to balance that, we need to multiply the whole half equation by 3. And then we would realize that we would change the number of coefficients gained, but we change the number of electrons gained to 3, but then that would mean we have 3 Ag plus 1s being reduced to form 3 Ags, or 3 Ag ions being reduced to form 3 Ag atoms. Then, to write the net ionic, all I do is I take all the reactants and put them on the reactant side. So I do Cr0 plus 3 electrons plus 3 Ag plus 1, and all the products and put it on the product side. Cr plus 3 electrons plus 3 Ag0. And then I cross out the electrons because they're the same on both sides. Watch how beautiful this is, though. So we have chromium, we have 1 chromium with a charge of 0, and we have 3 silvers with a charge of plus 1. So 3 times 1 is plus 3. So the net charge on the reactant side is plus 3. Over here I have 1 chromium with a plus 3 charge and 3 silvers with a 0 charge. So here I have 1 times plus 3 charge. I balanced the charges. In this reaction, electrons are transferred from. So who lost the electrons? Cr0. 2, who gained the electrons? Ag plus 1. Okay, voltaic versus electrolytic cells. We're going to do this really quick, but some very important things you need to remember. For both of them, you have to remember that the anox red cat, oxidation happens at the anode. Anox, anode, oxidation. Oxidation. I'm spelling it wrong. Oxidation. And at the cathode, reduction occurs. Always, any kind of cell, reduction, cathode, whether it's electrolytic or voltaic. The big differences here are the battery. In electrolysis, you have electrical energy being converted to chemical energy. And in a voltaic cell, it's spontaneous, whereas the electrolytic is not spontaneous. So you have chemical energy in the electrodes being converted to electrical energy. Now, we're not going to have time to go through this whole thing, but real quick, through the salt bridge, you need to have a salt bridge in the voltaic. Ions move in the salt bridge, ions migrate, and the idea is to balance the charges in the half cells. Okay, through the wire, electrons move. Why do electrons move in this case from zinc to copper? Because zinc is higher on table J. So if it's higher on table J, it's going to be oxidized, which means it's going to lose electrons. So the electrons are going to flow from the zinc to the copper. When the electrons flow from the zinc to the copper, the zinc atoms are going to become zinc ions as you lose electrons. So oxidation is happening here. This is oxidation. This is your anode, anox. Over here, the copper 2 plus, remember the Pac-Mans? The electrons are going to hang out on the electrode. The Cu2 plus is going to gain the electrons that are hanging out on the electrode, and the ions are going to become atoms. Therefore, the mass of the copper electrode is going to increase. Okay? Over here, when we talk about the electrolytic cell, the silver atoms over in the anode, this is going to be the anode, the silver atoms are going to be oxidized to form silver ions. How are they going to do that? The battery is going to pull the electrons away from the silver, and it's going to deposit them on the spoon that we wish to be silvered. Now, the silver ions then, this should say silver plus 1. Okay, the silver ions are then going to be in solution, and they're going to be repelled by the anode over to the cathode, where they're going to undergo reduction, and they're going to gain electrons to become silver atoms. One thing that we didn't really mention in class, this silver nitrate. It is very important that you have a soluble salt ionic compound in solution in an electrolytic cell, because you need to have moving ions. If it's insoluble, then you wouldn't have moving ions. So if there's a question, always check table F. Okay, I'm going to stop this one because we're at 30 minutes, and I'm going to do the last